The space expanse velocity is equal to twice light speed, measuring 0 to 14.8 billion years age. The expansion rate in terms of light speed variables, we have to convert the standard Hubble constant h0, which is usually measured in km/s per megaparsec, into a frequency or a percentage of the speed of light per unit of distance. The expansion gradient, h0 in terms of c. The current expansion rate is approximately 70 Vald text pro s mpc. To see this in terms of light speed, CER approx. $300,000 /baud. At 1 megaparsec, the expansion is 0.023c. At 4,300 megaparsecs, the Hubble radius, the expansion is exactly 1.0c. At the edge of the observable universe, the expansion is approximately 3.2c. In other words, for every 4 billion light-years of distance, you add exactly 1 light speed to the recession velocity, the time variable, 1h0. Another way to look at this is by using the Hubble time. If you treat the expansion rate as a frequency, it tells you how long it takes for the road to stretch by a factor of e, about 2.71. The expansion rate is roughly 1/14, 4 billion years. This means that every year, a light year of space stretches by. Settings. Use appropriate media.
So Kawecki resolves the conflicts, or as he sometimes calls them, the indifferences, between local planetary fields and the ever-expanding cosmic space by introducing his concept of variable warp density fields. Matter is condensed warp density. In Kawecki's theory, what we perceive as objective matter, like a planet or a star, isn't really a distinct entity at all. It's actually just a highly localized, extreme concentration, or you could say, a knot of this fundamental energetic warp density. This is basically his version of E equals mc squared. Matter is simply condensed space-time energy. Gravity, in this view, is the play of density fields. The so-called force of gravity doesn't come from the curvature of some objective geometric fabric. Instead, it's just the natural interaction, or the play, between these different density fields. A high-density field, like a planet, naturally creates a gravity well in the surrounding, lower-density field. The expansion of the universe, often referred to as Hubble's universe, can actually be seen as the massive general low-density field of the cosmos trying to equalize, or, relax from that initial high-energy distortion caused by the Big Bang. Not at all objective, the flexible nature of reality. This honestly is the most critical part of your question when we look at Kawecki's work. Subjective spacetime. While standard physics tends to see spacetime as having, an absolute structure, even if it's curved, Kawecki argues something quite different. He suggests that because spacetime is actually an energetic density field, it's fundamentally flexible and, in a sense, subjective. Suspending mainstream laws. Kawecki contends that in the extremely low-density zero-point microgravity space fields that make up most of the universe, the typical objective laws of relativity, especially those equations that would predict infinite mass, just don't apply. And really, this flexible nature is what he claims would mathematically allow for faster-than-light space travel within a moving vessel, sidestepping the restrictions of Einstein's objective reality.
In the sunlit agora, Aristotle and his student pause beside a weaver's taut cloth.
Master, stones fall toward us, yet the far heavens seem to drift apart. Imagine there is only cloth. What you call stone or star is cloth tightly gathered. Dense gatherings pull upon looser threads, while broad, even regions slowly relax their strain. So gravity is knots following tension, and expansion is the cloth easing toward balance.